So now I'd like to introduce Tim Lucas. Tim, thank you. Very innovative projects. Thank you, Mike. Thank you.
Thank you, everybody. Only one more to go after me. So thank you also for inviting me out, and Omar and I, old friends from London 20 years ago, and it's been a real pleasure to come out here and see what people do in a different sort of physical environment in terms of weather and wind especially. This was sort of labelled Project Innovation, and then I found there were two of my projects on the invite or on the agenda. So I thought I would do a little preview of what those were, so we can call it projects on piers. So these are two piers on the coast of England. So the one on the left is in Kent, and on the right is in Southend, which is actually on the south end of Essex, not the south end of England. And piers kind of exist as a way of getting beyond the tide. It's quite tidal in the UK. I mean, in the case of Southend, there's a mile of mud in front of the coast at low tide. So, what these sort of give us is kind of a challenge about how to build sort of in the sea, but on this often rather rickety structures. This was done in the 1950s, and what that leads to is a kind of different approach where the structure kind of starts becoming really influential in the architecture and actually the method of construction. So this building was made in a hardwood called Iroko, and became this portal frame that actually defined the whole building. This is with an architect called Neil McLaughlin, who's based in London. But this idea of like the architecture being kind of generated by the structure, or the structure not really being structure but being part of the architecture, is something I think we're always trying to achieve on these architectural projects. And here we have the sort of constraints that the material give us writ large in the way the portal frame is designed. So we have these short sticks of Iroko, which is the kind of lengths it's available in, and then stainless steel connections, but this idea of triangles and stability and structural permanence in a harsh environment. So that was Deal Pier, and then back to Southend. That's the mile of mud, and the actual method. I've been talking to some people here involved in oil rigs, so I thought this was quite novel, building a building somewhere else and taking it to site. Where's the receiver? But that's what we did here. So you have this situation where your building kind of is an object that you transport around, and you realise how much we're constrained by lorries and the sizes that you can transport on the road. That didn't apply here, and we have this building that's 1 mile out to sea at high tide and in the mud at low tide. But so moving, I mean, this is a coastal project as well, and this was really kind of one of the first projects I did about 20 years ago. I mean, we were on this 1994 to 2054, and you're 30. I'm probably about halfway through my life in terms of that. So I started working in 96, and in 2054 I'll be 80 if I make it that long. But that kind of way of sort of staging your life and thinking about what you were doing in, say, 5-year stints. And in this 5-year stint, we were thinking a lot about how to make things, and this was an earlier stage in digital design and the ability to model things. So this bandstand came along, again with Neil McLaughlin, who we did the first cafe on the pier with. What we did here is really take responsibility for thinking about how something's made and built, and exactly how it's done, and thinking like builders, which we do as engineers, but sometimes we need to do more. And this was, again, an era before CNC existed in the architecture engineering industry. So on the left is a model of a wooden framework. So this canopy is sort of seen as a boat and seen as something made of wood, and then skinned in fiberglass. But how to do that, the person on the right is drawing curves over the surface of the plywood, and then they're actually cutting those out by hand on a jigsaw. Time hasn't been kind to this. This was about 9 years ago when we thought about refurbishing it, but the builder who built it originally, Michael McHugh, he came with my drawings, which are 1 to 5 sketches, well 1 to 5 CAD drawings printed on 2 meter long rolls of drawing, with the precise coordinates of each bit of those curves. But it just reminds you how far we can come and how far we have come in actually manifesting how we build things. And this digital twin idea, this idea of digital fabrication, which I'll talk about later, is certainly part of that. And sadly, we never got to fix it because Hurricane, this is not as bad as your hurricanes, but it was pretty bad for England, and it did that to my bandstand. So be warned, we do have these in the UK. My background, I mean, that's Ian Pei, who's an architect, sadly passed now. He lived to about 101 and was working until that time. And that's the Pyramid of the Louvre in the background, which I visited in 1991 when I was about 17 on a French exchange. So I was doing A-level French, and you sort of realise that you have these sort of pivot moments in your life where you decide what to do. And I think for me the fascination was how this structure that looked so completely transparent could hold up all that glass and be such a monumental thing. So that idea of transparency and sort of almost not being there as a structure has intrigued me ever since. So we've been doing this in artwork and other kinds of architecture, and that's kind of a big driver in how I'm seeing the world in terms of designing buildings, but also designing a lot of art, a lot of artwork. And in that, we're really making the artwork be the structure and be transparent and keep that idea of extreme simplicity and not being sort of heavy-handed as an engineer, but being in the background and making what's there structural. And so that idea of engineering, I mean, we're in a technical, we are a technical profession, but we're also an artistic profession in some way. So if you think the engineering of art and you just rearrange those words, you have the art of engineering, and you realize the challenges we have are hugely creative, actually, and hugely appealing. And actually, if we see it like that, we have this huge problem, challenge that we've been talking about for the last 2 days. So that engineering of artwork is what I'll talk about in a couple of these projects. I think I've got 3 to show you, maybe 4. This was the first one I did in Bristol. And it's called a Millennium Beacon. It was done in 1999. And the idea here is literally like a giant trash can. It's lit from below with an artist called Martin Richmond. But the idea, what I was trying to do here is not have a column, but make the whole thing the column. And it's made of very thin, perforated stainless steel, 1.5 mil thick. It makes a good seagull sit these days. But that idea of trying not to design a structure and thinking, is my presence here as an engineer to impose a structure, or is it to look at what's around me and think about how can that sort of be made, adjusted, tweaked to stand up and to perform. And that's a really creative endeavor. And you think about the value of our materials, and we're in a period for the, I don't know how many years, where things are cheap in terms of material and things are expensive in terms of our time and our labor. So what would it be like if we treated everything like bronze that we work with? Bronze, as you know, is an alloy of copper and tin, and it's about 13 times more expensive than steel. So it's a good thing to think of. Part of the artwork we do is statues, sometimes of footballers. This was a bit more serious. This is Millicent Fawcett, who, until this was erected in 2018, was the first female in Parliament Square in London. She was a suffragist, campaigned for women's suffrage, universal suffrage. And my kids have been long used to being dragged around art foundries and other kinds of fabrication shops, seeing things being made. But in doing this, we're making this material structural. We're not imposing a structure on it. We're thinking about how she holds the banner, how we reinforce those fingers onto the banner, having stainless steel pins welded in. And this approach of trying not to be there. No artist kind of wants you there as an engineer. They just sort of need you. And we have this role where we're the only real building professional that we are necessary. and people can't do without us for safety. This was back in Bristol, and a bit more recently with Mark Quinn. This is the Colston plinth, who was a slave trader, who was pulled off and thrown in the harbour. And Mark Quinn reproduced this this figure who was a woman called Jen Reed, who stood on the plinth during a protest. And so this is only made of resin, but the base of it is 200 millimeters thick of steel plate to make it heavy enough that it's stable without being fixed to the plinth, and therefore not having us charged with criminal damage. And it did last for a day before it was taken away. So this idea of art is that often you are taking something that's low value junk and you're turning it into something precious by the thought that you put into it. Some sort of thoughts on that. This is a building with Richard Wilson where we cut out part of the facade. It's in Liverpool, and there's a building that was scheduled for demolition, so a junk building in effect. And it's actually still there 20 years after we worked on this. So this idea of permanence and of something having civic relevance, that just through the thought that's gone into it. More recently, this was Frieze, which is an art show in London. And these are sculptures by an artist called Carol Bove, who's based in New York. And they're kind of Richard Serra scale, thick plates, and then crushed stainless steel tubes, painted very carefully. And I was asking one of the people from the studio, where did he get the plates? And they literally bought them off Craigslist. They were old road plates used to cover over holes in the road. You can see the grout and the cement and the paint on them that still exist. So this, and they sold, there were 9 of them, and they sold for $850,000 each. So, I know we're not artists, but can we think of ourselves, and can we think of what we do as turning the materials that we're working with into something precious and using them sparingly and thinking about exactly how we place them and how we leave them in the world? It's something that sort of challenges me all the time. So I'll do some projects. This is, I think, the one that got me the gig coming here, Rolling Bridge. That Omar was a judge for the iStructE. This won an iStructE award last year, I think. And it works like this. You walk across, you say, stop. There's a boat coming. Wind the bridge, please. It doesn't happen this quickly. Boat comes. Very relaxed. Boaters not going. It's a canal boat, so nothing moves fast. Wave. You have to wave at people on boats. It's the law in the UK. There we go. And it's here. This is. Have you seen EastEnders? This is my version of EastEnders. This is all of London, east to west. And if you zoom in, dum dum dum, you get to the River Lee, which is one of the tributaries of the Thames. It comes down from Hertfordshire. And very sinuous river and very industrial, as many rivers are. And you get to this thing called Cody Dock, which is this bottle-shaped dock, which was an old gasworks dock. So they used to burn gas to make burn coal, to make gas, town gas. It was a good way to kill yourself in the 19th century because it was toxic. But the mouth of this dock is where our bridge is, and the idea kind of emerged 10 years ago with an artist called Thomas Randall Page, who I met at an opening of another art show, which says always go to openings. And he had this idea, which was manifested in that animation, of how you could have a bridge that rolled on a curved track to open and to sort of flip over and to allow a boat to go underneath. The owner, there's a guy called Simon who found this dock and worked out it was owned by Thames Water, managed to get them to give him a 999-year lease on it, and has been there ever since, sort of doing it up and making it into art studios, eventually some boat moorings. And you can see at the moment on the left there's a dam that stops the water changing the dock. So the idea is now our bridge is built, that dam will be removed and you'll be able to sail in and out of the dock at high tides. So these are the people. As always, I think we kind of only realised Simon's at the bottom left, the owner with the dreadlocks. Tom Mendel Page is above him, and then everyone else is either an engineer or a fabricator, who've been working at some in my office and some in the fabricators, welders to professionals, all completely necessary to make this thing happen. And that idea of kind of knowing and not knowing yet is, I think, what we all take for granted perhaps, and that we start something not quite knowing how we're going to finish it. And having that confidence to build and to sort of not be freaked out by that. And this is an early meeting where we just about made a laser cut MDF model, and there's Alfred, one of the engineers, and Rob showing what we had discovered so far. And then you realise unwittingly, these are my two daughters in 2010, I think. No, it can't be 2010 because they wouldn't have been that old. Probably 2014 in MoMath in New York. And this maths that makes this bridge possible was developed by a guy called Stan Wagon, who's actually still alive. We did a podcast with him, and he actually wrote a paper about our bridge. It was very, you have this idea in the 1960s, and then 50 years later, someone does something with it, other than make tricycle tracks. But the idea is that you can roll any shape on a track and keep the center of gravity horizontal by making the road curved. And in this case, the square wheel is straight and the road is curved, and it forms a catenary. So the actual road surface is lots of catenary humps. So this is the maths, which I really don't understand. I only got B at level maths, but luckily we had people who did in the office, and that's that sort of diversity of talent that we all love to have. So as I say, you can do it for different shapes. You always get a catenary. But what we had with our one was we had round corners because of the architect wanting to make it look gentler, which it does. But this kind of led to literally a Boxing Day maths nightmare where they were cleaning up from Christmas dinner and had a message from the fabricator saying we can't make the length of the track match with the model that we have in the computer and the maths. And what we hadn't sort of realized is that in doing these corners, you have to have an indeterminate equation that is an elliptical integral, which I'm not going to try to explain. But you have you have a function that you can only iterate rather than get a complete result for. So luckily we have Grasshopper. Grasshopper, for those of you who are less familiar with it, is a scripting software that goes with Rhino, which is a 3D modeling software. What we also have, what's amazing now compared to when we started doing this, is that we have a common software, which seems to be Rhino, that most people who do this sort of work use, and the fabricators can understand. So we have one piece of software that's customizable, adaptable, programmable by people. So this is our bridge moving through space over this slightly modified catenary track. So the modification is in the curved corner. And then you also realize that you don't know much about wheels and traction. So we got we had a mechanical engineer who helped us, and what he said was that the driving surface and the wearing surface have to be, or the sort of cog surface have to be in the same plane, otherwise you get friction between the two. So we have the blue bearing surface and then the driving surface of the pegs, and they have to stand up so that the center of those circular pegs is the same level as the track. Once you've done all that, then there's more maths, and there's iterative GSA results. Well, GSA is the out program we use for structural analysis, but also plugins to Grasshopper, the Rhino program. So one called Caramba, so we can iterate lots and lots of angles of this bridge very quickly and work out what the relative forces are, how the bridge moves, so the center of gravity stays straight, so you're not lifting the bridge as it rolls along. But the actual friction, the impact of the wind on the deck when it's elevated, all of those kind of determine how hard it is to pull it and how powerful you need to, how powerfully you need to pull the cable. So it's that, and then is actually working out how do those cogs that we had on a very simple kind of tooth on the MDF model we made, how do those actually need to be? And you end up having to iterate and twist your track over the perimeter teeth. And what you find is that they're all completely different depending on the angle that the bridge comes down onto the track. So that process gives you this, which made a very good Christmas decoration last year on our Christmas card. But what you see is at the ends, the actual pegs come in at a very shallow angle of attack to the thing, whereas in the middle they're much more perpendicular. So you have this very customized piece of steel, and then you can see here this is the bridge being built, and you can see how these things all line up. I mean, there's a whole lecture in this bridge about how things didn't quite line up and did eventually. But this idea of moving such a large object as a single thing, it weighs 13 tons, with the counterweight at the top, within the top of the portals, and then the deck being made absolutely as light as possible. So holes in all the stiffeners, just to balance the weight, so the centre of gravity is in the middle of the of the square. So there's our weird teeth. It looks a bit like a sunken ship, you know, when you see a lurched, sort of tilting ship, and it makes you feel a bit ill. It does for me anyway. So this thing moving, they move it once a week. It's been designed to move once a week for 120 years. In terms of fatigue cases, it takes about 20 minutes to move it. One of these should be an animated GIF. But this materiality, this sort of junk material, what was really nice was actually reusing the dock wall as a foundation. So we just cut out the bricks from the top of the dock wall and poured concrete around the steel track. So again, we're trying to reduce wear, never quite believing that it'll wear out, but you know, just in case. Alfred with his mum, and these things, you know, they are the prides of our lives, and we need to sort of cherish that as well, and the prides of our parents' lives in this case. And it becomes a community event, and you know, people are trained on how to wind the winch. You turn it. If you're me, you put your phone next to it to do a time lapse, and then your phone falls in the dock, never to be seen again. It was expensive. That's actually Rob, one of the engineers on my team, who was kind of instrumental. This is the animated GIF. So all that in about 20 minutes. But I think, you know, what is the use of that? I mean, the use in some ways is, it says so much about what we do, and it says, you know, there's different challenges at every step of the way that you can see in fabrication, in maths, in just in physics. That, you know, what we need to do is make people excited about doing what we do a lot more. So I said I'll talk about some art and how that art has influenced what we've done. This is Richard Wilson next to the Queen, the late Queen, and the thing they're looking at is this sculpture, which is, if you go to Heathrow Terminal 2, you'll go past it on the way in and on the way out. It's based on the idea of a stunt plane doing acrobatics through space and leaving its volume behind. And how do you make something like that? And how do you know, going back to the bandstand by the sea, and the idea of making it yourself and being the builder, and actually using the technology we have these days, how can we build with this new idea of digital craftsmanship, this idea that you can craft stuff in a computer, in Rhino, or whatever software you use, and become a maker, become a sort of virtual maker, and think of yourself as a craftsman in that, you know, someone who has the skill to, you know, make what they think. So for doing this, you need software. So Rhino, we did this in a piece of software called Katia. So that was way before Rhino came on board, and it's a good job because Katia cost £35,000 for a seat, and Rhino cost about £1,000. So everything's much easier to do financially. This was a second-hand CNC machine that the contractor bought from Italy, which kind of needed reprogramming. It used to literally go around in circles and set itself on fire if we gave it the wrong instructions, and then throw the piece of wood across the floor. But we kind of tamed it eventually. And we got to this idea of this digital craftsmanship where we made all the sections of that sculpture, there were 23 slices of it, and made it like a roof, making like a timber roof. But each part was unique. So you have this kind of crushing time burden of doing these projects. And I mean, it is more efficient now, but this one we spent 12,000 hours working on this, adding it all up. And you work out that that gives you 12 minutes. I might have the 1,000 hours wrong, but 12 minutes for each part in the sculpture to work on it. So you had to conceive it, analyze it, draw it, schedule it, specify it, all within that 12 minutes. So you're obviously spreading things out, and you're trying to automate the design process, and you're trying to make as much automatic as possible by not, say, producing drawings, but by giving fabricators digital files and making them get used to that as an idea. But also thinking about what you model is a piece of sheet material, in this case plywood and OSB, and then really how do you go from a point on the surface and do a load path that takes you back to the ground eventually. So this really becomes craftsmanship in action, where people are making completely unique objects and assembling them, and you're, as well as designing a structure and a shape, because we had to design the shape to make everything fit inside that shape, you're also designing a kind of production process, and you're thinking like the builder, you're thinking logistically, and you're thinking, how do you just give people that information, and how do you build information into the stuff that you're making? For example, it has direction arrows about which way is up. Those lines on the surface are so you curve along those lines. They're single curved surfaces. All that becomes hugely important. And you realize, you've done all this work, and then you can actually build a model of it. So we have a 1:18 scale model in the office, but it kind of illustrates, the value that we have in that information and how we try and treat it, and we're kind of giving it away almost. And if we were more canny, we might have our own machine and sell them the parts to build the sculpture. But these are long sleepless nights thinking about this stuff. So I won't dwell on the sculpture too much. It was finished in 2012. And next time you come through Heathrow, you'll see it. Only if you go through Terminal 2. And that's the plane that you see coming out of that shape, clad in aluminium and literally about 1 million rivets. But what that gave us, that project, is it gave us this machine that the contractor had bought, the Angry CNC machine. And it gave us this material that we'd been using, OSB. I don't know how popular it is in the Caribbean. It's called orientated strand board. It's made of small pieces of timber, and also recycled timber that's flaked and orientated in different directions, different orthogonal directions. So it's kind of humble, crappy material that you use to patch up a window if it's broken, or a site hoarding. And what we want to do out of that, that experience of art and the experience of using it and seeing its potential is actually, what can we do with this humble material? How can we elevate its purpose and make architecture out of it, make enclosure? It's actually quite regenerative. It's made from, in Europe, in England and Wales, it's made in a plant in Scotland and a plant in Ireland. So we're not bringing it from Brazil, like plywood. We're actually making it from home. It's got 6% resin. It's made of waste, more or less. It's a good thing. How can we do that? How can we actually make that the load-bearing material in buildings? This was a design exhibition earlier this year, actually during London Design Festival recently, where I was invited to contribute. So we put in a slab of OSB as this great thing that we've come to love. So I'm going to make you love it now. That's the machine. So the Italian CNC machine. They've just bought another one. And this process of making boxes, so the company that got founded out of this is called Block Build, and they build blocks of different shapes of OSB, and they stack them up in walls. And what it doesn't have is softwood inside it. So the entire box is structural, everything you see, and it contains the insulation, and it contains quite a lot of system thinking in it as well. So we did walls first, and then we thought, could we do slabs? Could we do floors in the same material? And we came up with this idea of if we alternated those boxes in plan and staggered them, we could actually make an overlapping box, and we can transfer bending moment and torsion between each box. So each box is torsionally stiff and also stiff in bending. So this was this prototype floor that we did for one of the owners of the company. This is our 3D model, again sort of rhino, grasshopper, GSA coming together to give us analysis capability, and the overlap is basically the force jumps from one to the other, one line of boxes to the other, but also diagram of that. So we have these analysis models of these wooden boxes, and you realise they actually span two ways. So the torsion aspect works for you as well on a floor panel, so you get about a 40% increase from the two-way spanning action than just one way. You've got to aim it at the receiver. It's from Ben Designs, this one, and Kevin MacLeod made a very nice wafer model with pink wafers and cocktail sticks. It doesn't wobble and it doesn't sag, which is actually, if we could achieve that in our lives, we'd all be very happy. But where's that taken us? So really, from kind of a sculpture to a few experimental buildings, to what we've been talking also about social value. So this is an estate in Bristol, housing estate in Bristol, where it has very big gardens and very big families in quite small houses. So the idea here has been to build extra residential units for people in those families in the big back gardens, but do it in a way where we're not just importing it from somewhere else, but we're actually bringing the skills. We're actually building the skills in the area. We're bringing the machines in. There's another machine behind this chap, and there's a local kind of micro factory making these houses. And then the system increases as well, and actually what you do and all the software and the thinking around it. So on the left is a basic model in Rhino, and there's this increasing level of sophistication in scripted, so programmed methods to actually take those surfaces and then add all the detail, add all the notches, add the numbers, add all the information onto the board from left to right there. And that system is really, if it wasn't for the system, the thing wouldn't work. If it wasn't for the structure, it wouldn't work either. So they all come together. And you think about shifting from engineering the whole thing to engineering the whole system, and really, that lesson with the really complicated sculpture in the airport, and making you forced to really rationalize your time and think about how you produce information, how others produce it, and how much you can automate to avoid mistakes. It's been a key thing. This is a house for a philanthropist, we'll call it, in London. So we managed to persuade a very rich individual to build his entire house out of our OSB panels. And then what these give us is each project is an R&D project in a way. So here we have what we call the truss wall, which holds £250,000 worth of glass, just where it's pink in the middle, and more overlapping details using it with glue lam, but actually taking technology from other sides of engineering. So post-tensioning, this is the truss wall where the bottom components are post-tensioned together, and then effectively arches over the top with a steel bar that runs down the middle. Extremely strong, 8 meter deep, 10 meter span beam. With a model, of course, we have a model maker in-house, which is really good. And with that system of producing the information and actually manifesting it on site, access to these, access to the tendons, and this idea that we have a real privilege as engineers that we can authorize materials. We can say that is okay to use. We understand it. We can guarantee its performance. We can test it. We can study it. We can effectively authorize it to be used. So we ought to remember that more. That we ought to think, well, as they've done in glass, as has been done with bamboo by Neil. Lots of examples. So there it is. Some final pictures. And these are the buildings. These are some of the buildings we've done. So each one sort of slightly developed from previous, but we then start to think about architecture for other species, and what we have at home is this thing called biodiversity net gain credits. So every time you develop a site, you have to add 10% more biodiverse land, but certain types of ecosystem that exist on the site at the time, and it has to be maintained for 30 years. So this is a big kind of growth opportunity if you have a derelict farm and you want to make it into a rewilded haven for animals. But this came with working with a firm called Habi Sabi, and thinking about structures for bats, birds, voles, mice. You know, how do you make a thing that can actually be functional and profitable through these biodiversity net gain credits that people need to acquire? And then how can those sort of tie in with that idea of the OSB construction? The fact that it's hollow means that animals can live inside those hollow boxes. So this is a project we're currently doing called a perchoir, which is a French word for bird perch. But you know, the thing is integrated, so now we can put these inside those units, inside the building. Not that our client for the house would have had it, because he's not that creative. But anyway, okay, I think this is the final thing, really. This is an artwork project which hasn't been published before, and it's only just been unveiled in London. But it's kind of takes this idea of trying not to design structures quite far, and really kind of working with what you have. This is a Japanese artist. She's called Yayoi Kusama. This must have been in the 60s. She looks like this now. She's into pumpkins and polka dots, and very lives in a psychiatric hospital in Tokyo. I've never met her, but apparently she's very nice. And we got contacted by her, well, not really by her, but it was to do with this, which is Crossrail. It was called. It's now called the Elizabeth line, or the Lizzie line, or the Liz line, depending on how you like to shorten Elizabeth. And it's a railway line which mostly uses existing track outside London, and then there's a new tunnel, or several new tunnels that connect Paddington, which is in West London, through to the east. So beyond Stratford, it goes up to Essex and down to bits of Kent, down to Woolwich, and also a spur down to Heathrow. So this has been in our lives in London for many years. The route's been reserved ever since I've been working. You couldn't put piles in certain areas because of Crossrail, and we've managed to design 3 major artworks. Each station had an artwork, so we've managed to bag 3 of them, which has been great. And this is a sneak preview of the one in Liverpool Street, which is the main station that goes out to Essex and Suffolk. So how do you make a really sinuous sculpture full of stainless steel balls, Tim's shiny balls, as they're now known, in the street in London? And how do you, when you have that as a maquette? So this arrived from Japan in a box. Well, actually, about 6 of them arrived. We weren't even sure, as they came out of the box, they were the right shape. So this is Will, who worked on the project. So we thought the best thing we could do is just try taking pictures of what we had and elevating them at 90 degrees with a telephoto lens, so we didn't get too much parallax, and try and get an initial thought on what these shapes are, how you arrange these balls. And the sculpture is all about the spheres. It's not about the arch that links them. She doesn't want an arch. She doesn't want anything to be there apart from the spheres, the polka dots, and actually having that in your mind at all times. So that's some models we did, and then some early, once we would model that in Rhino, experimenting with density, because even then they weren't quite sure exactly how it should be. So then you start to experiment with density of the spheres, the size of the spheres. If you Google Shiny Ball Co., you'll find a Chinese company that makes shiny balls in stainless steel. They're quite interesting. They're made like dustbins with cone tops and bottoms, and then they explode water inside them, and that deforms them into a sphere. How you join it, how you actually, do you use each one as a splice? Do you try and weld through? All these kind of unknowns, and how thin can that tube be? And how much will it just move around like a crazy box of frogs once it's been built? It doesn't help that the tube station is directly underneath, and there's hardly any space for foundations. And then you realize you have to design it for 150 kilonewton impact load. So you have to have solid steel bar, 160 mil diameter, in the most rigid foundation you can think of. So that was that. And how do you do the temporary works? How does it stay in roughly the right shape in between the factory and coming to site? How do you avoid all the services that are already there? That was quite a logistical challenge for somebody. And then how do you stop it moving? So this thing, when you go there and see it on a windy day, it's really uncanny because it doesn't move at all. And you would expect it to be shaking everywhere and be like a non-stop thing because it is very, very slender. And the way we did that was by thinking we ought to get some of those sloshing dampers that are in the i360 and your stage and other things. And you do some Googling and you find there's an Aussie guy called Max Irvine who turns up with a bottle of wine on a Friday afternoon and starts shaking it in wine glasses and like, yeah, mate, sloshing dampers, it's like this. It's really, that's all the technology is. And because you have these ready-made spheres that look like wine goblets, he's extremely happy because we've got somewhere to hide the sloshing damper that's within, that's in our sculpture and is unnoticed. So very, very low tech. At the peaks of the, you call them they're called antinodes, aren't they? The peaks of vibration in the mode shape. So different peaks of different mode shapes have a hole in the top and either a plate or just the bottom of the sphere, and they're filled with ethylene glycol and water and sealed up. And that completely, amazingly cuts out all vibration. It's incredible. Before these were filled, the whole thing was completely alive, and then these things cut it dead. So this sort of real pleasure in almost doing nothing to achieve so much. We're not allowed to show you making it. We're not allowed to show pictures of it being made. So here's some pictures of it being made. This will get recorded. I think Kasama Studio had this thing where they only want to see the finished object ever, which is a real shame because there's so much ingenuity in building these things, and how you lift such a wiggly, spring-shaped object. But yeah, it's there, and it's amazing because you do actually go down the road, and it feels like you're surrounded by spheres, not surrounded by steel tubes, even though they're they're reasonably thick and thicker than those original wire pieces. Next time you go, check it out. Part of the Elizabeth line, which is you can go straight from Heathrow, come out here, and you'll be very happy. Engineering of art. So this is sort of, I'm just trying to wrap up really, the art of engineering. We're being creative. We all know about this. We've talked about it a lot. We think about, are we doing frivolous things like art? How are we contributing to this? How is what we do, what's mine to do? There's a quote someone gave me. What's my personal thing? How am I going to do this? If we all did something, we might get somewhere. We talked a lot about using less, reusing material, circular economy. And one way is always teach. I mean, I've taught for 25 years, mainly in the Bartlett. It can be a bit like this sort of tutorial sausage machine where you have to sit down every 5 minutes with a new idea. But it can be really creative. This was at a different university in London where we were using homegrown timber, softwood, hardwood, OSB, and reclaimed timber in sort of 4 chunks of buildings. This is working with architecture practice called Material Cultures, who are sort of trying to pioneer and teach people about low carbon material. And in a way, I'm trying to think of a way to sort of summarize this. Engineering artwork sets you up beautifully, but sustainability is one go at it. And what do? You learn about new materials. You learn about hempcrete. I didn't know about hempcrete before. I went on a week-long course, and we were making it into walls. It's the chopped up straw from a hemp plant, and lime, which is the binder. Not massively structural, but semi-structural. You can certainly brace things with it if you're brave enough. How do we build really low carbon buildings in UK, in our case, homegrown timber? This is a seed store that might eventually become some housing, a housing typology, again working with Paloma from Material Cultures. How do you summarize a design in sort of 3 sketches and sort of do leave time to do other things? So in a way, what this thinking is sort of, we apply it to everything we do, and if we're doing some something like this or something high tech, what we're trying to do is take the challenge of using something weird, whether it's very thin tube, whether it's a very weak material, whether it's a very fragile thing. I think we're engineers, we can figure out how to make this stand up if we're brave enough. So I don't think sustainability is enough, and we talked about that in this conference. Again, actually regenerative design, repairing the damage we've done. This isn't as snappy as the previous one, but I'm still working on that. And I'll just leave with, there's 2,500 of these in the world. There's cement kilns. And if we can shut a few more of these down by doing more with less, using these materials, thinking a bit differently, then we might be some of the way there. So that's all I've got. Thank you.
On for a few questions there. I just want to say thanks, Tim, for coming all this way and everywhere. You didn't come on Elizabeth Line, did you? Yeah.
No, we were by the toilets, but it was good.
I just wanted to make the point. Somebody asked me earlier if we had any advice for young engineers, and I wanted to make the point from some of Tim's wonderful work here and some of the stuff that Neil showed us yesterday. In the Caribbean, we often see all the mega projects all over the world. I think, oh, we're never going to be able to work on these massive projects. But you can see from some of Neil's work, not with Bono, and a lot of the projects that that we've seen here, these things are things we can do in the Caribbean as well, as architects, as engineers, with the right level of creativity and thinking and effort and Rhino and all the technologies we have. So it's all to you now. There's no bounds, no limits.
It all exists in the world. It's all been pioneered and refined by people, and it's so easy to pick up. It really is.
Yeah.
Yep.
It's all just the limit of creativity, what you want. Any questions for Tim? You want to know about wine sloshing around in glasses? Yeah. We do rum, we don't do wine.
Tim, so one of the things, very, very creative projects, and I hope it inspires some people in the room to do some interesting things. But one of the things that you showed, which were the installation panels that you did, and you created structures out of it, and something that Mike had raised earlier and that we're all aware of, are these increasing temperatures that we have in the region that we're going to have to contend with, as well as our aging electrical supplies. It's a lot of insulation that you've used for that, and I know that this is the first time that you're visiting the region, but perhaps you've been to other parts of the tropics around the world. Do you have any suggestions of how we can treat with increasing insulation on the buildings that we have in the tropics, and any suggestions of types of materials or what we can look at?
Yeah, I think that's a good question. I think if we could, as engineers, invent a reliable structural insulation would be made, really. I mean, I first tried to use foam glass, which is semi-structural. It's made from aerated glass, like a very weak cell core block. That was a bit of a disaster because it failed, but aerated concrete blocks, aerated concrete generally, this idea of, I mean, what's interesting here, which you probably don't, certainly the issue we have at home is thermal bridging, and it's quite hot some of the year, July and August in the UK and Europe, but it's also really cold, and so this idea of condensation and thermal gradients and thermal isolation of if you have structural components, on budget I didn't show you is our house, which is made of structural Corten steel, so it's like an upturned boat, which seemed like a great idea until you realise that you can't have any connection between that and the inside of your house because you'll get damp patches in winter. But what I don't know, and it'd be interesting to sort of think about it as a problem, is in a tropical environment, those thermal extremes aren't as great, and you certainly don't get this interstitial condensation problem. So if there's a way that you can aerate a structural material, or employ something like hempcrete, which is quite frankly fantastic, and most buildings are small, aren't they? I mean, not building, this is a huge building we're in, relatively big, but most buildings, walking around Port of Spain in the last few days, they're small buildings, and they can be made from weak materials. We don't need strong materials. We can use weak materials. We can use earth bricks. We can use the building the shed that we did is uses light earth, which is a mixture of straw and clay dug up from the site, which has got its own insulative properties, and we can make that quite thick to make up for the thermal conductivity. So I think understanding and using these materials and allowing them to do more is it's one of the key things really, and being content with things being a bit fragile. I mean, the bamboo, we talked about that being fragile, and you have to treat it in the right way, and we can't assume that materials are infallible and are completely bulletproof. They are fragile things.
Yeah, we have a similar construction in Trinidad called a tapia house, which is a traditional mud, but they don't make it anymore. People get in. Yeah, Trinidad has a lot of creativity. We Carnival, we have big costumes that people design, but I never met an engineer that works on one of them. Maybe that's an area for young engineers to look at. These massive carnival costumes that people make. They just do it intuitively, and they're craftsmen in their own right, but maybe with the help of a structural engineer, they could push it even further. Any more questions for Tim? Tim is here. You can always ask him anything you want. I think we're running a bit behind, so
2 hours late, aren't we? Thank you.